Hello, I am JD and you are listening to The Ongoing. Last episode, we talked about how batteries work, how chemistry makes electrons move, how rechargeable batteries send material back and forth inside the system. And we ended with a problem. Devices were becoming smaller and more portable, but the batteries could not keep up. Making them bigger was not a solution. Something had to change. So scientists began asking what material could store more energy without adding weight. And one material stood out: lithium. Lithium is the lightest metal that exists, and it gives up electrons very easily. Those two things together meant something important. It could store a lot of energy without adding a lot of weight. That's a rare combination. But turning that combination into a safe and reliable battery was not a straight path. It took 3 decades and 3 scientists, each asking a different question, to finally get there. But before we get into that, a quick reminder of how a battery works. A battery has 2 sides. On one side, atoms give up electrons, become ions, and move to the other side. Those electrons travel through the circuit, and that flow of electron is electricity. And when you charge the battery, those ions move back, the system resets. Now back to lithium. In early 1970s, this combination suddenly felt very urgent. Lithium was lightweight. It gave up electrons easily, and the world needed better batteries. Oil prices were soaring. Small electronic devices were becoming part of everyday life. Even oil companies started thinking about this. One of them was Exxon, and one of their scientists working in New Jersey was named M. Stanley Whittingham. Whittingham joined Exxon's research lab in New Jersey in 1972. And by the end of that year, he had already built something remarkable. On one side of his battery, he used lithium metal. On the other side, he used a material called titanium disulfide. Titanium disulfide has a layered structure. Think of it like a very thin stack of sheets with tiny spaces between them. When the battery was used, lithium gave up its electrons, became ions, and traveled across to the other side, into those tiny spaces inside the titanium disulfide. And when the battery was charged, those ions moved back. And it worked. Whittingham's battery produced around 2.5 volts. Existing batteries at the time produced only 1.3 volts. With this new battery, that was nearly doubled. It was lighter and stored significantly more energy. But there was a problem. When the battery charged, the lithium ions traveled back to the lithium metal side, and when they arrived, they did not settle smoothly. Instead, tiny spikes of lithium metal began to form, like little needles growing inside the battery. These are called dendrites. Over time, those spikes got bigger, and if they grew large enough, they could connect both sides of the battery. When that happened, the battery could short circuit, it could overheat, and in some cases, it could catch fire. So the battery worked, but it was not safe. And eventually, Exxon walked away from it. The idea was real, but there was something fundamentally wrong, and nobody had solved it yet. In 1980, another scientist took the next step. His name was John B. Goodenough. Goodenough was working at Oxford University in England as a head of the inorganic chemistry laboratory. He studied Whittingham's work carefully, and he focused on the other side of the battery, the side that received the lithium ions. Whittingham had used titanium disulfide there. Goodenough had a theory. If you replaced that material with an oxide, a compound built around oxygen rather than sulfur, you could get a much higher voltage. And more voltage means more energy. So he began researching, systematically testing different materials. And in 1980, he found one that worked: lithium cobalt oxide. Like titanium disulfide, lithium cobalt oxide had a layered structure. Lithium ions could move into its spaces, settle there, and move back out again. But the numbers were very different. Whittingham battery produced 2.5 volts. Goodenough's material could produce up to 4 volts. That was not a small improvement. That was a transformation. More voltage meant the battery could store significantly more energy in the same amount of space. But the dendrite problem remained, because lithium metal was still being used on the other side. So when the battery charged, lithium still came back as metal, and metal still formed those spikes. The battery was better, but the root cause of the problem had not been touched. And that's where Akira Yoshino came in. Yoshino was a Japanese chemist working at Asahi in Japan. he looked at the dendrite problem and asked something different. Can lithium never become metal again when it comes back? Because that was the root cause. Yoshino found a material called petroleum coke, a byproduct of oil refining. Like lithium cobalt oxide, petroleum coke has a layered structure, with spaces between those layers. And here is what made it special. In those spaces, lithium can sit as a loosely bound ion. Not free, not fully bound, but loosely bound. Not metal, just an ion, gently held in those spaces. So when the battery charged and lithium came back, it did not come back as metal. It came back as a loosely bound ion, settling into those spaces and staying there. The dendrite problem was solved. The battery was stable and it was safe. In 1985, Yoshino filed the patent. But a patent is not a product. It took years of engineering, testing, and manufacturing work before it was ready. And then, in 1991, Sony released the first commercial lithium-ion battery inside a portable video camera called the Handycam. Small, lightweight, rechargeable, safe. That moment quietly changed everything. In 2019, the Nobel Prize in Chemistry was awarded to all three: Whittingham, Goodenough, and Yoshino. Three people working separately across 3 different decades, each solving one piece of the puzzle. The breakthrough wasn't just finding the right materials. It was finding the right questions. It required someone at each step to look at what everyone else had accepted and ask, does it have to be this way? That's it for today. And that's also the end of our 2-part story on lithium. It was a longer journey than usual, but it deserved the time. From a frog's leg twitching in a laboratory, to Volta's first steady current, to rechargeable batteries, to a battery that quietly changed everything. Thanks for listening. I am JD, and this is The Ongoing.